Okay, okay. All right, so for A, it's negative 43,545 volts. For point B, almost negative 5,000 volts. And they're both negative because our negative charge was bigger, twice as big, right? Negative 2 versus a positive 1, twice as big. But our distance didn't change by very much. We're far away, and so the distance didn't change by very much. So the charge ended up sort of dominating, and the negative one was providing more potential at that location than the positive one. So they both end up negative when we add them together. But there are positions, if we started maybe over here, we're much closer to Q1 than we are to Q2, so the potential would probably be positive at that location. Right? There are positions that have positive potential. We just happen to pick two that both have negative potential. But that doesn't matter, because what we really care about is the change in potential as we go from one place to another. It's similar to, if I drop this pen, I say, now you'd use potential energy, right, not potential. I'd say I have some initial potential energy. If I call the table 0, I have some initial potential energy, and I drop it, and I can take the change in height, right, and I can figure out the change in energy and how fast my pen's going. Maybe you pick the floor as having 0 potential energy, so your starting energy is much more than mine, right? We both have different values, but your ending energy is also different than mine, but we both have the same delta. We both get the same answer for the speed of the pen right before it hits the table. Potential is the same way. What really matters is changes. The 0 is kind of arbitrary. We pick a 0 that just happens to work out nice mathematically usually. For a point charge, the potential goes as 1 over r. Right? Potential goes as 1 over r. So a nice place mathematically to pick 0 is r equals infinity, right? 1 over r, 1 over infinity goes to 0 as you go to infinity. So that's what we do for a point charge. We say the potential is 0 at infinity. For other charge distributions, that doesn't work as nicely. Like for cylindrical charge distribution, if you had a long, thin rod of charge, then picking 0 at infinity doesn't work as nicely mathematically, so we usually pick some other location. But for point charges, it works out very nicely, so we pick that. It's arbitrary. Okay. So we're good with that. We've got our two potentials. Now we want to find the work done. Students always ask me, what's the work done? Is it Q delta V, or is it negative Q delta V? And of course I say, yes. It depends, right? Are you talking about the work done by the field or the work done by the external force? Some books write it this way. Some books write it that way. I say don't worry about the sign. The magnitude of the work done is Q delta V. Then think about the sign later. We already thought about the sign. Is the field doing positive work? Is the field pushing it that way? In this case, we said the field was doing negative work, so we know our work done by the field has to be negative. The work done by the external force is going to be the other equation, right? One of them is the field, one of them is the external force. It has to be positive. So let's just find the magnitude of the work done and then make sure that the field is, what did I say? Field's negative, yeah, and the work done by the external force is positive. Because those are opposite, equal and opposite. You understand that? Because our particle started and ended at rest, the field is going to either push on it or pull on it as it moves. Right? In our case, the field is pulling it back towards its starting point. So we have to reach in and push it. We have to reach in with an external force and push that particle. And what do? We let up a little bit at the end and let the field pull back so that it's at rest at the end. It started and ended at rest, So the work done, the net work done has to be 0 because there's no change in kinetic energy, right? Work equals change in kinetic energy. If we were going the other way, if we let go of it at point B, the field would start it moving in this direction, and it would start going faster and faster and faster, and it would try to go past point A with some speed, right? Because the field's pushing on it the whole way. It wants to get it closer to the positive charge. If we had it constrained on a rod here, right, it would get pushed in this direction. But we don't want it to end up here with some final velocity. We want it to end up here with at rest. So what do? We reach in with an external force and push back and slow it down so it comes to rest right there. So the field does positive work pushing it in that direction, and our external force does negative work pushing against it, slowing it down, bringing it back to rest. And those have to be equal in magnitude because it started and ended at rest. There's no change in kinetic energy. So let's find that. What is it? So magnitude of the work done, Q delta V. The charge we're moving, what are we moving? A -3 and delta V is final minus initial. I'll just write it out. VB minus VA, final minus initial. In this case, this is positive, so this has to be the work done by our external force. What'd you get? That's joules. And then, so that's work done, what do we say, by the external force? Okay. Good review? Okay, so again, I think I said that the true benefit of using electric potential, you have to introduce it and kind of learn what it is, but the true benefit, the real advantage in using it comes in circuits. And so we're not there yet. That's the next chapter, right? And so I think when we start to do circuits and you start to see how we use it in circuits, it'll be, oh, yeah, okay, this kind of makes sense now. But in addition to some of these problems, there are a number of examples. Let me just kind of rattle through a couple. So, obviously it makes this type of problem easier if you're moving the same charge, if you're moving different charges from point A to point B over and over again, then you don't want to have to figure out the work done, right? If every time you moved a charge from point A to point B it was a different magnitude charge, you wouldn't want to have to do that calculation over and over and over again. So what do? You do the calculation once, figure out what delta V is, and then every time you move a different charge from point A to point B, you just multiply delta V by a different charge. It's a lot easier that way. And that's where are the charges changing all the time? In a circuit, that often happens, right? The charges are always changing. So that's why we use this in a circuit. Okay. Other applications. Neurons, right? Electrical signals. So how does that information move from neuron to neuron? So how can we see? How can we hear? How can we get our muscles to contract and move around? It's all because of potential differences generated in the neurons, the action potential, things like that.
Is that what membrane potential means when you talk about the body?
Yeah, it's an electric potential difference caused by the buildup of ions inside the cell, right? And you can it's an electrical potential difference, yeah. Resting potential, right? There's the cell moves ions in and out to maintain a certain potential. And then there are other medical applications, EEGs, EKGs, things like that. We can look at these signals inside the body and look for abnormalities. So a number of interesting applications there, especially in a lot of you are interested in the human body, medical applications.